Welcome to the STEM Pathways with Rohan Sharma podcast. Today I'll be interviewing Steve Reinhardt, who holds a PhD in computer science from UW-Madison. How are you doing today?
Doing great. Thanks. Thanks for having me on, Rohan.
Yeah. So to get started, I wanted to ask what your interests were back in high school and what led you to choosing your major for your undergrad.
Yeah, well, back in high school, that was back in the early 80s. I was fortunate that my parents got me a Radio Shack TRS-80 computer, so I had been playing around with that. Some of my friends had computers too, Apple IIs and such. So I'd done a little bit of programming, so I was definitely interested in computers, but I wasn't really sure. So I thought I might be interested in physics as well. So I ended up deciding to major in electrical engineering because to me that seemed like I was kind of splitting the difference between physics and computer science. Um,
So when you got into college, did you realize that it was the right decision like right away, or did it take a while?
yeah, I think I enjoyed it at first. I mean, being an electrical engineer, there's a lot of like calculus and signals and systems and circuits and things like that. And I guess I did realize eventually that I liked the computer side of things better. And so I ended up, even though my degree was in electrical engineering, nearly all of my electives were in computer engineering or computer science. So I think by the time I finished my undergrad, I knew that I wanted to do something with computers.
And what led you to liking the more computer engineering stuff?
That's a good question. I think to me the sort of digital binary nature of things like logic are come more naturally than things like calculus and currents and such. And I really enjoyed programming. Low level programming is a lot of fun. Understanding where the kind of digital logic meets the programmability and how that builds up into like a software stack, I think is just really appeals to me for some reason.
And are there any things from back then compared to today, especially like during college, that look very different for students who are doing things with logic gates and digital design?
Oh, I'm sure. One of the big things that we had back then was breadboards. So if you took a digital logic design class, you would plug little ICs onto these white breadboards that had all the connections. Then you would use physical wires to connect pins together, and it was a very very tangible way to build a circuit, but it was also very error prone, and the connections would get flaky. So it could be very frustrating. Whereas now today, everything is with simulation or FPGAs, if not, and so it's a lot cleaner today, I think, than it was back then.
So during your undergrad, were there any activities you're involved in outside of class?
Um, Not a lot, to be honest. We and engineering was pretty intense. We had some kind of intramural sports and things that I participated in my dorm, but nothing really big, actually.
So when did you decide that you wanted to go on and do a master's?
Yeah, actually, that's a interesting story. I wasn't really sure. I kind of, made a mistake and got lucky in a sense that I wasn't sure if I wanted to go to graduate school or get a job. And so I only applied for like the really premium jobs because I thought, well, if I don't get a good job, I'll just go to grad school. And I only applied to a few of the top grad schools because I thought, well, if I don't get into a good grad school, I'll just get a job. And it ended up I got exactly one job offer and exactly one grad school acceptance. And the amazing thing is the job offer I got was from Bell Communications Research, which was a kind of a spinoff of Bell Labs, and they had a program where they would send you to get a master's degree for a year before you started full time. So through that program, I was able to both accept the one job offer I had and the one acceptance offer that I got, which was to Stanford, and get a master's degree at Stanford, which was really great because I ended up taking the couple of computer architecture classes from John Hennessy. And, for those of you who don't know, he's the co-author of the primary textbooks in the field, and ended up as president of Stanford University. But at that time, he hadn't even written the book yet. I think this was a year before he wrote the first. He and Dave Patterson wrote the first textbook, so it was all out of like his notes. And I just connected with the material really in a really deep way, and knew that that's kind of what I wanted to do, was design computers.
Mhm. And was Bell Labs also in the Stanford area then?
This was actually in New Jersey. Bell Labs and Bell Communications Research were both in New Jersey. So this was a year full-time school away from the job. It was a very a unique program. I don't think they do it anymore, actually.
Mhm. So how has computer architecture changed from back then to today?
It's changed quite a bit. I mean, especially back when I started, computer architecture we were in the middle of sort of the RISC revolution, and there's a lot of emphasis on things like instruction set design and pipelining, and yeah, compilers being able to replace people writing assembly language by hand was kind of a new thing, and so it was very kind of at a much smaller scale. Whereas now we see, right, we have things like, CPUs with hundreds of cores on them, or over 100 cores. We have, GPUs. We have, not just compilers, but we have AI generating code. And so the complexity of systems is much, much higher. And so I think but at the same time, some of these things like instruction set design, nobody really worries about that very much anymore, especially on the CPU side. So the topics of emphasis, I think, have changed, even though the idea is still like, how do we integrate hardware and software? How do we build interfaces between hardware and software that get the most out of both?
So during your master's, did you decide immediately that you wanted to do a PhD, or did that take a while?
No, that actually took a while as well. So I got my master's, and went back to work at Bell Communications Research, and then realized it was very fluky. Back in the '80s, you probably don't know much about this, but AT&T used to be a monopoly, and there was a very big deal about the breakup of the AT&T monopoly, and they wanted to be kind of unrestricted and not have to deal with all the constraints that were on them. But one of the things that came out of that whole transition from the monopoly to the kind of breakup of AT&T was that they were not allowed to build computers, because there was a big fear that if AT&T was such a dominant company, if they built computers, they would just take over the computer industry. So as part of the settlement with the government, when they went through that transition. So it was very ironic that after I went to Stanford and realized, hey, I really want to do computer design, and I came back and I realized I was working at pretty much the only place in the country that was forbidden by law from designing computers. So after a while, I moved on. I went to a Data General, which was a mini computer company in Massachusetts. And I was there for a few years, and there was a very rocky transition. Microprocessors were kind of moving up the stack and killing off the mini computers, and mainframes and things like that. So there was a bit of a recession. Data General wasn't doing well. Digital Equipment, which was, of course, the big company in Massachusetts at that time, was also laying off. So that's when I decided, maybe since I wasn't very happy with my job and the prospects of finding another one weren't very good, I thought, well, I'll just go back and get my PhD. So that's when I looked around. I kind of looked at where the interesting work was being done. I applied to a few places, including Madison, and got a good offer from Madison, and very glad that I went there.
So what was your research about during your PhD?
My research was about parallel computing. There was, this idea of kind of microprocessors taking off was pretty clear at that point, and so the understanding was that more powerful computers, would really be built by uh, combining lots of microprocessors together into multiprocessors. But of course, at that time, a single core was just a single chip. So we didn't single chip multiprocessor. So we had to build them up by connecting lots of individual processors. And how you do that, how those communicate, what that looks like, how you coordinate the shared memory or message passing or what have you, was kind of a big research topic at the time. So I ended up doing my thesis in kind of a technique for distributed shared memory across large numbers of microprocessors.
So what was your first job out of your PhD?
My first job out of my PhD was as an assistant professor at the University of Michigan. I really had no intention or thought of becoming a professor throughout most of my childhood or even when most of graduate school. But it turned out, when I graduated, looking at jobs in the industry, they were pretty concentrated geographically. Like I felt like I could move to the Bay Area, or I had an offer from IBM Watson in New York, and neither of those were places I really wanted to live. And so I realized that, hey, if I wanted to have some choice in terms of where I lived with my family, I should consider a faculty position. And also, I had some advisors at Wisconsin, David Wood, Mark Hill, Jim Laris, that made being a faculty member look attractive. They managed to do it well. So I thought I'd give it a try. Got an offer from Michigan, so I went there.
And how long were you professor for?
About 10 years.
Oh, what kind of courses were you teaching?
Um, I taught a couple of different courses kind of in the architecture area. At the undergrad level, I taught a undergrad microprocessor design lab. So this is one where kind of, had an embedded systems flavor to it. The lab had these FPGAs with embedded microprocessors in them, and the labs would involve building peripherals and integrating with the peripherals, talking to the peripherals from software on the microprocessor. So people got to understand that connection between software and the physical world. And later on, we added a project at the end. So people did some pretty cool, embedded system type projects in the course. At the graduate level, I taught the kind of introductory graduate architecture class. I also taught an upper level class on parallel architecture.
So after talking to some other professors, a lot of them said that even after being a professor for a long time, their teaching hadn't changed too much until AI became a thing very recently. Now that you have industry experience, is there anything you think professors should be doing to teach their students differently now that we have AI?
That's a great question. I haven't really thought too much about it. I've felt maybe a little bit fortunate that I don't have to deal with the changes in education that are coming because of AI, because I'm sure it's it's got to be a huge shift. I think, I've always had this, the challenge in terms of wanting students to want to understand things, and I think inspiring students to learn in a way other than being very strict about testing and stuff. It would be very nice. I do recall one time when I had a student, come in and was complaining about his grade on a test or something like that. And I told him, look, I don't want to give you a bad grade either. I don't, my goal in life is not to, give out bad grades. I really want you to learn the material. And if there's a way to get you to learn the material without making you take a test at the end, I would gladly do that. But I don't know of one. And so I felt like the student was really kind of surprised to learn that mostly I just wanted them to learn the material. I didn't really want to be going through all the processes of administering tests and giving out grades. But that's kind of the only way to force people to actually learn things, it turns out.
And then also without skipping ahead too much, um,
Uh,
now that AI has become a thing in industry, are there any new skills that you think students should be learning?
yeah, I do think that I mean, working with AI, it's very challenging in the sense that working with AI and understanding the capabilities and leveraging it for your own self education and for doing the work that you need to do is critical. Um, whether it's just developing code or exploring ideas or looking for related work on a topic or synthesizing work, it's it's just invaluable. And it's hard to say given how much things have changed even in the last year. Say, where is this going? Where is it in? Where is it going to end up? What are the right techniques to teach people to do this while still kind of forcing them to think for themselves at some level? I think that's a very big challenge, and I don't have the answers.
So what'd you do after being a professor at UMich?
So after I left Michigan, I ended up at AMD Research, and AMD was just kind of starting their research division at that time, and so I was one of the relatively early members of AMD Research, and that was a lot of fun. We ended up getting an early grant from the Department of Energy to work on exascale supercomputing. At the time, that was far off in the future, and the government was kind of encouraging companies to look ahead in that HPC space. And it was great. At the time, AMD was going through some pretty rough times, and we managed to get this grant. And it ended up, after I left AMD, that AMD won the contract to build Frontier, which was the first exascale supercomputer that the government built. And so it turned out to be the beginning of a very fruitful direction for AMD. So and it was also part of the big shift from kind of CPU centric computing to more GPU centric computing. AMD had at that time had recently bought ATI, so they had access to all of this GPU IP, and along with NVIDIA, we were kind of pushing this direction of using GPUs for dense compute as accelerators rather than trying to do everything on the CPU as kind of vector CPUs is what had been used in the past for high performance computing.
So was a supercomputer back then kind of just like a tiny data center?
Um, yes and no. I mean, I think there were a few different directions that were converging. I mean, if you go back to the 70s and the 80s and the classic Cray machines, I mean, those were very exotic technology. A lot of them were liquid cooled or used, very kind of high performance circuit techniques, and had very very big vector engines on them as well to make them go fast. That was kind of the focus of the Cray design. And so they were in this. So then there was a phase where the microprocessors started taking over, and people started building some microprocessors with big vector engines and tying those together to make supercomputers. And then really the next transition was going from this kind of vector augmented microprocessor base to the GPU base as the kind of the foundation of the compute horsepower. I mean, from a sufficient distance, they look a little bit like data centers in the sense that you have all of these high performance computers strung together very very closely. But typically in an HPC system, the network that connects the processors is much higher performance, much lower latency, much more tightly integrated into the processor than it is in a standard, like say an Azure data center or something, where these things are typically tied together with like an Ethernet network. Actually, I would say the actual trend now is with AI and AI training and these big clusters of GPUs to do training and inference. What's happening is that actually data centers are starting to look more like high performance supercomputers than the other way around.
Mhm. And what were these supercomputers being used for?
Um, a lot of simulation, mostly science experimentation. The Department of Energy actually has two main users of supercomputers. There's the Office of Science, where they do a lot of simulation, things like climate change, material science, combustion, um, astrophysics, all sorts of things like that. And then there's the other side where they use them a lot for nuclear weapons design and testing. So the kind of the classified side is all kind of revolves around nuclear weapons.
So what'd you do after being at AMD?
Well, after I was at AMD for a while, I got the opportunity to go to Microsoft. They were or had just been ramping up this new idea of saying, hey, we're going to put a lot of FPGAs in our data centers, and that's going to give us this programmable hardware fabric that we can use to accelerate compute. I think they saw that the compute demand was rising, and that this would be an efficient way to address that in a flexible way. And so one of the big users of this technology was Bing. There are a lot of like PageRank type algorithms in Bing, and that they had accelerated with these FPGAs. So I had the opportunity to go to Microsoft and basically run the FPGA team inside of Bing that was supporting Bing algorithms.
And at this job and your last job, something that I've been asking people recently is if there's ever something that they didn't like about their job that
Mm.
either led to them switching up how they did their job or even switching jobs. Was there anything that you ever didn't like?
Um, I mean, I think there's always, no job is perfect, but generally, I don't think I've left a job because I really didn't like the job. I think I've always, when I've changed jobs, it's always because I found a better opportunity somewhere else. And some of that kind of coincides with the opportunities changing in your current situation. So, for example, after I was at Microsoft for 7 years, the FPGA program started to kind of wind down, and Microsoft started to focus more on their in-house ASIC development. And so the job that I was doing was kind of going away. And so even though it was a great job and I loved it while it lasted, that opportunity was kind of drying up. And so that's when I looked at what else I might do, both within Microsoft and outside. And the opportunity to come back to AMD on the AI side came up. And so I took that.
And then were there any day-to-day things that you just noticed you ever didn't enjoy about anything, like any specific tasks that you just noticed were kind of a drag for you?
Oh, there's always things that are sort of, you might consider them, necessary evil type things. I mean, not even evil, but still just a drag. I think things like, reporting to your manager and kind of collating what everybody's doing, and giving reports, going to status meetings, things like that. Of course, your management needs to know what you're doing, and needs to appreciate what you're doing, but it always feels like all this communication, managing communication between teams, between people, between layers of the organizational hierarchy. It's necessary, but it feels like overhead sometimes.
Mhm. And since you've had a lot of time leading like big teams of engineers, the more you've done it, are there any specific skills that you think you've gotten that have helped you do it better?
Um, that's a great question. I think some of the things that I've learned are the necessity of giving clear feedback. I think I'm it's always difficult to have a conversation where you're telling somebody that you're not happy with them or that they didn't do a good enough job. But that's something that you have to figure out how to do if you want to be a good manager, because sometimes it's necessary. Um, and I think also just being uh, being human, right? I think people aren't robots. They have good days and bad days, and um, bad things happen in their lives, and good things happen in their lives, and you don't want to kind of overstep any boundaries, but at the same time, you want to acknowledge that, and make sure that these people are appreciated, as people, and not only for the work that they're doing.
So what was your role after Microsoft?
So after Microsoft, now I came to my current job, which is in the AI group at AMD. It was kind of interesting when I went to Microsoft. I didn't know anything about AI, and even I think even when I interviewed for the position, they didn't really say much about AI. It was all just about these FPGA acceleration of various algorithms. And then when I got to Microsoft, it turns out, the one thing that everybody wanted to accelerate at that point, and this was, 2016, 2017, was AI. And so they had just kind of discovered, a lot of these early AI algorithms. This was before the transformer. So these were, RNNs and things like that. And FPGAs were actually very good at executing these neural networks. And Bing uses a lot of neural networks for a lot of different pieces, things like recognizing, is your query a local query or a fact-based query, or how do we categorize it? And so I learned a lot about AI, and then transformers came along, and we kind of had to pivot our accelerator that we had designed for the FPGA to supporting transformers, because everybody wanted transformers when those came out. And then I was very fortunate that I was still there when Microsoft started to roll out GitHub Copilot, which was really the very first kind of generative LLM based service that anybody tried to deploy at scale. And so it was, I sort of learned a lot in the process of seeing that happen. And then it was really having that experience of looking at, of seeing a generative AI cloud service being deployed that helped me to come back to AMD on the AI side of the fence, as opposed to on the research side of the fence. And now I lead a team that does performance modeling and analysis and optimization for AI models on our GPUs.
So what does this modeling look like? How do you go about doing that?
Yeah, that's a great question. So really, you look at the AI model, and you can break it down into components. There are the matrix multiplications, and then the kind of element-wise vector operators and things like that. And then you can also, if it's a multiple GPU, if it's spread across multiple GPUs, you have to look at how the data is laid out and how it's communicated, what those communication patterns and operations are. And then you can build up a model that says, okay, I know that this step takes this many operations and this many bytes, and I know that this processor is capable of doing this many operations per second and reading this many bytes per second out of memory. So you can kind of compute how fast a model should run on a particular machine with a particular set of parameters. And so we, inside of AMD, we have several fairly sophisticated tools that do this kind of thing, and they're useful both for taking existing machines and existing models and saying, well, how fast should this run? And then if you look at how fast it actually runs and it's not that fast, you say, okay, well, we've got some work to do. Here's where we need to optimize this to use the full potential of the hardware. And then, or you can also look at models that don't exist yet on hardware that doesn't exist yet. So certainly when we're planning out our, next generation or generation after that GPUs, we use these same models to say, okay, we can sort of extrapolate that in 2 years we think LLM is going to look like this, with this many parameters and this many experts and things, and we project that the design we built can have these parameters, and then we can run through these performance models to say, okay, what do we think the performance is going to be, and is that good enough? And if we have a choice of going this way versus that way, which one gives us the better performance or meets whatever we think the customer expectations are going to be.
And then how like explorative is the work you're doing right now? Is this stuff that's being implemented like as you do it? Or are you looking at stuff that's kind of in the future?
We're kind of in the middle. I think my team is in a position that I really appreciate. We're not one of the engineering teams that's generating the parts of the ROCm software stack, but we're not in research, so we're not looking out at these very speculative things. We're really trying to stay maybe one step ahead of the product teams in terms of looking at what's coming next, but in a very short-term fashion. What do we have to get ready for? What techniques can we use? Of course, right now we're also very involved in building agentic AI tools to do some of this work as well. So yeah, like I said, it's kind of filling that gap, I think, between the short term product engineering and the sort of longer term, more speculative research space.
So if you had to go back to college and you wanted to get into the field now, what do you think, what are like the main entry level jobs that students should look at?
That's a great question. I think things are changing quickly these days. Certainly within AMD, we're still very eager for people who both understand AI at a reasonable level and understand how computers work, basically, right? So a lot of this work in terms of saying, hey, how do I optimize a particular model to run on a piece of hardware, or how do I design a piece of hardware to run a particular model optimally? I mean, there's a lot of work on automating that design process through AI, but I think it's still an area where you can't just sit back and let the agent do it for you. You have to really understand what direction you're heading, and maybe the AI can help you with some of the details and some of the comparisons. But unless you have a basic understanding of um, kind of this combination of algorithms and distributed systems and hardware architecture, you can't really put it all together, I don't think.
So for my last question, I wanted to ask if you have one piece of advice for someone who's still in high school or college wanting to follow a similar career path as you.
Yeah, I think looking back over my career, I think a key thing is really to make the most of the opportunities that you get. I think some people try to sort of plan everything out, early on. They say, oh, I know I want to do this, and then I want to do that. Life changes a lot. Both, personal circumstances and also technology. I mean, 10 years ago, I never would have imagined that I would be doing AI. I don't think many people would have imagined that AI would become, what it's become. So I think all of the kind of main transitions in my career have been cases where I was presented with an opportunity that looked interesting, but of course always involved some risk. But I took those opportunities, and when the risk was reasonable, and they've largely paid off. Certainly, I think by going from AMD to Microsoft, I ended up learning a lot more about AI than I probably would have if I had stayed at Microsoft or stayed at AMD. I mean, and so then I was able to go back to AMD and maybe with kind of more value than if I had stayed the whole time. Um, and similarly with being a professor, I hadn't intended to go to be a professor, but the opportunity came, and I enjoyed it a lot, and I'm really glad that I did it. But then, I had other opportunities that took me away from that, and so I'm just really grateful for all the different parts of my career that I've been able to have.
All right, then. Thank you for joining me on the podcast today.
Sure, thanks for having me, Ron. Really appreciate it.